familiar quantity first. We define a vector. A vector is, I can simply write it as A and a symbol on A like this. Okay, this is a vector, but if you choose a particular basis, then you can write its components. A vector is independent of basis, but the components depends on the basis that you choose. So, if a basis is chosen, then this vector can be written as, so let's say we choose a basis which we call it as E alpha, then this A can be written as A alpha E. So this A alpha are called components of a vector in the basis. In the basis here. Is it readable to the back? You can read it. Now, I have written the components. Here this alpha I have written in the superscript. Okay, I do not want to write it as a subscript, you will understand why. But let me now say that I will write always a superscript here and a subscript here. The basis, the index is always on the subscript. So this you have to learn as some kind of a religion. In Tensor we are going to follow these rules. Okay, why? Because there is some convenience, there is some agreement that we should follow these kind of rules. So the basis, we are going to have a subscript alpha. What is alpha? Alpha is an index which will take values 1, 2, 3 if you are having a Cartesian 3-dimensional coordinate space, or it can take 0, 1, 2, 3 if you have a special relativistic 4-dimensional space-time. That is unimportant for us at this moment. So alpha will take values depending on what is your space. So alpha just is an index, and the coordinates I will denote them with superscript. And sometimes, because I am going to use it like this is also called the components of the vector A in the basis E alpha, called as contravariant components. Contravariant components. I will come back to the definition that is given in books like Afghan, that contravariant components are the ones which will transform like a coordinate, covariant components are the ones which will transform like derivative and so on. So we will come to that. We will try to understand that after developing some notation. When I write like this, there is also another thing that I follow, is that repeated indices, these notations are due to Einstein. Repeated indices with 1 in the superscript and the other in the subscript are summed over. This is called Einstein convention or Einstein summation convention. So that means there is one superscript here, one subscript here. This is alpha, this is also alpha. This essentially means this is sum over alpha, A alpha, E alpha. Where alpha will go from 1 to 3 if you have a 3-dimensional space, or 0, 1, 2, 3 if you have a 4-dimensional space time. Okay. So alpha is equal to 1, 2, 3 in 3-dimensional Euclidean space. Or alpha is equal to 0, 1, 2, 3 in 4-dimensional space time, which is what we deal in relativity. Okay, now I can define, so this is a vector. Then I define another quantity which also looks like a vector, but it is slightly different from vector. We will not be able to appreciate the difference in this at this point, but let me define it. In mathematics, this is known as one form. One form is a scalar value function of a vector. When I say scalar valued function of a vector, what does it mean? It means that, now imagine this function is like a box. You give some input to get some output. So if you give input as, normally a function itself can be visualized like that. You give x as an input, you will get f of x as an output, right? If you say f of x is equal to 2x, you give x is equal to 1, you will get 2. 2, you will get 4, and so on. So you can, this visualization will help us in understanding more generalizations of this concept. So you can say that we have the one form is a scalar valued function of. So if I say that I have f of x is equal to 2x. Okay, if I have this function, then x is also a scalar and f of x is also a scalar. Correct? So we can say this is a scalar valued function of a scalar variable. Because input is also a scalar, output is also a scalar. So you can call this one as scalar valued function scalar valued function of a scalar. So one form is a scalar valued function of a vector. That means if you give vector as an input, you will get a scalar. Okay, so we can write, so that means you have something called one form is like f of some vector v is equal to some scalar alpha. I should not use alpha here, so maybe let me use some p is equal to f of v. So v is a vector. So this is a vector and this is a scalar. Okay, so this is also called, of course, a one form is, I must also add here another term, it's a linear scalar value function. It's a linear scalar value function. That means if I have two vectors, that means f of v1 plus v2, if these two are vectors, this is the sum of these two will be another vector, and this can be written as f of v1 plus f of v2. So if it is a linear function, then this will be satisfied. In addition, if we have f of some scalar r times v, will be r times f of. If these two properties are satisfied, then we say here is linear.
Both must be satisfied.
Yeah. You can write them as one property, like if you can write it as, you can combine them and then say that f of r1 v1 plus r2 v2 should be equal to r1 times f of v1 plus r2 times f of v2. So this contains both these things. Now you can say that there is one way this one form is defined as, what is the way you can generate a scalar from a vector? We can use an inner product, right? You can define an inner product of a vector with another vector. Okay, so if I say that I have, so let me use this notation P. So a little bit of so I will say P of V. P of V, I will use a notation called a tilde on this, saying that this is not a vector, but this is a one form, is equal to the inner product of P and V. Or I simply can write it as a bracket. There is also another language which is used for this quantity, namely a linear scalar valued function of a vector is also called a linear function. A linear scalar valued function of a vector is also called a linear function. So one form is a linear function. That's it. Okay. So one form but you can have some general linear functionals which probably are not one forms. Okay, so linear functional is again defining a scalar from a given vector. Okay, you can say that I think there is no difference in Tensor. You can prove a theorem that every linear functional f of v can be written as f of v is equal to, so let me write it in the context of vectors. This is the inner product for vectors. F of v is a dot v for for some A. Now proof of this theorem is elementary. Let us assume that we choose a basis, then V can be written as V1 times E1 plus V2 times E2. Let's, for the time being, assume only 3-dimensional space, E3 times E3, then f of v, I can write this one, and linearity will tell me that it is v1 times f of e1 plus v2 times f of e2 plus v3 times f of e. Correct? It's a linear functional, so I can write it like this. Now, E1 is a vector, so f of E1 is a scalar. So I will call that one as A1. Okay? So this is equal to V alpha A alpha, V alpha A1 plus V2 A2 plus V3 A2. So this is basically, this is nothing but A dot B.
So, how do we know f of D1 vector is also a functional.
The f is a functional. So whatever the vector goes as an input, I get a scalar. Okay, I'm calling that scalar as A1. So this proof, this tells you that linear functional is same as one form. Every linear functional can be visualized as a one.
So you said that one form is a linear functional. The converse is also.
That's what I proved. So you say you have an arbitrary linear functional, it can always be written as a dot product through this. So choosing a basis, I have proved this. I proved this, but it doesn't depend on the choice of the basis. It's arbitrary.
Means every linear functional is a one.
Is a one.
You mentioned there's some general functional something like that you mentioned.
I thought that maybe not all linear functions are one forms, but now we have proved that it is. So I didn't remember this theorem when I said that.